This session will be by Zhenyu, and it is about scaling abstraction refinement for program analyses using graph neural networks.
Okay, thanks for your introduction. Hello, everyone. I'm Zhenyu from Peking University, and I'm honored to be here today to present our work. This is a joint work with Zhang and Peng. And selecting good abstractions is a crucial problem in program analysis. Abstractions that are too precise tend to be slow, while coarse abstractions are often too imprecise, which means that they will introduce too many false alarms into the analysis. So, it's important to choose abstractions that balance precision and efficiency, which means that it could eliminate most false alarms and run fast. Abstraction refinement is a method to find abstractions that are just precise enough. We start with the most coarse abstraction and run the analysis with it. Based on the result, we then select a more precise abstraction of the analysis. This procedure repeats until the abstraction is precise enough. Since we terminate once the abstraction is precise enough, the abstraction will not be overly precise. So, many abstraction refinement methods model the refinement selection as SAT or SMT problems. For example, one of the state-of-the-art abstraction refinement approach models the refinement selection as weighted max set problems, which tries to maximize the weighted sum of satisfied clauses. By solving the problem, it finds a minimal refinement to try. Since solving max set problems is NP hard, this approach is unscalable for large programs. Furthermore, the max set solver works in a greedy manner and cannot predict the effect after refining certain parameters, so it provides suboptimal refinements. Since neural network has shown its amazing power in many fields, our initial motivation is to use neural network to determine refinements. However, we face two main challenges. The first is that there are too many different analyses, and different analyses require different domain knowledge. So, how to develop a technique that could be applied to different analyses without feature engineering is a challenge. Second, neural networks are good at learning, so they can distinguish helpful parameters from unhelpful ones. However, in most cases, refining parts of those helpful parameters is enough, while refining them all can result in an overly precise abstraction which runs slow. So, using neural networks alone does not work quite well. To tackle the generality challenge, we found that Datalog is a logical programming language which makes it suitable for implementing program analysis, so that different analyses in Datalog can all be represented as hypergraphs, which can then be transformed into graphs without feature engineering. So we can deal with those graphs using graph neural networks. Then, instead of using graph neural networks to determine exact refinements, we use their output to prune those max set problems, so that we can get problems that are much simpler. And by learning from helpful refinements, the result of graph neural networks can exclude some suboptimal solutions. Finally, we will use a max set solver to target the exact refinement. So, our main contribution is proposing a general framework that could be applied to different analyses without feature engineering. To tackle the generality issue, we make use of the calculation of Datalog, which does not require feature engineering. and to make abstraction refinement scalable. To make abstraction refinement scalable, we use graph neural networks to simplify those maxset problems. And to find exact refinements, we use a maxset solver to determine refinements based on the output of the neural network. And to train our neural network, we design an algorithm to determine helpful refinements as our training data. Here is a pointer analysis example. There is an interface named dog, and two classes implement it. For every variable, pointer analysis calculates what objects it may point to. For example, since there is a new statement, variable teddy1 may point to a teddy object. For the assignment, every fact about teddy1 will be copied to temp. And how could we deal with function calls? Here, we invoke a function named id1, which simply returns its parameter. A straightforward idea is to treat parameter passing and return as assignments so that we could deal with them in the same way we deal with assignments. However, this is imprecise. Suppose another function also calls id1. Since there are two data flows into arg1 with different objects, arg1 may point to both a teddy object or a corgi object. So does teddy2. This brings in some imprecision, which is undesirable. The imprecision occurs because we use context insensitivity, which is a coarse abstraction. To improve the precision, we could use context sensitivity. First, we mark function invocations here from IA to IC. Then, we can distinguish different invocations to ID1 by considering it as two functions, so that the result of teddy2 will not be affected, and we can now get precise outputs. And though context sensitivity improves the precision of program analysis, it also increases the time cost of the analysis. It's practically impossible to use the most precise abstraction. Therefore, we need to select components to be analyzed precisely. For example, only refining IA here is precise enough. However, if we choose IC, since refining IC cannot improve the precision, so it's an unhelpful refinement. So we hope our neural network can figure out this. And to implement the pointer analysis in Datalog, we can implement its core rule as one Datalog rule, which means that if a variable u can point to an object obj, and there is a data flow from u to v, then the variable v may also point to the object obj. And information about the program under analysis can be represented as facts and rules. For example, the new instruction can be a points to tuple, and the assignment can be considered as a data flow tuple, while the function call can be considered as multiple rules under the insensitive version and the sensitive version. And Datalog will treat points to facts as vertices and treat those propagation between facts as hyperedges. Those abstraction parameters will be represented as vertices as well. And the Datalog engine will calculate new tuples based on the rules we mentioned before until it reaches a fixed point. Therefore, selecting different parameters will affect rules applied and then affect the precision and the result of our analysis. Our graph neural network makes use of the hypergraphs of Datalog. But since graph neural networks deal with graphs better, we need to transform hypergraphs into graphs first. Firstly, we replace every hyperedge with bidirectional edges from every head to every tail. And since neural networks need real vectors for calculation, we assign each vertex a feature vector based on its relation name, because relation names are general among different programs. In these programs, we have points to, we have data flow, and in the another program, as long as we are still running pointer analysis, those relation names still exist. So after training the neural network on a program, it can learn how to behave on other programs. So after the transformation, we use a graph neural network to process this graph, which calculates new feature vectors based on the graph structure. Then we use the final feature vectors of parameter vertices to classify whether they are helpful or not. So back to the example. Though the MaxS solver cannot distinguish unhelpful parameters, our neural network may say that IC is unhelpful. So we can prune out IC, and the MaxS solver will choose either IA or IB, and it will be an effective refinement. So to train our neural network to distinguish helpful refinements, we take the refinement trace and then cancel the refinement one by one. For example, to check whether P1 is helpful, we remove P1 from the last abstraction, which is precise enough to eliminate all false alarms. Since in the new abstraction, all false alarms can still be eliminated, so we can mark P1 as unhelpful. For P2, the abstraction after removing it fails to eliminate one false alarm, so P2 here will be considered helpful. Then we collect those helpful refinements as our training set. To experimentally show the effectiveness of our framework, firstly, we check whether our framework truly improves the scalability of old work. Second, we compared the precision of our approach to a state-of-the-art pointer analysis. Then, we inspect the number of parameters pruned out. Since neural network can make mistakes, we check how often and how much precision loss are there. Lastly, we illustrate that using neural network alone does not work well, so our combination of GNN and MaxS solver is necessary. We use two analyses to illustrate our ideas, and we will show the results of the pointer analysis. For the scalability, we select benchmarks that the baseline approach will time out, and we train 3 neural networks using 3 different training sets. Here, blue bars stand for the baseline approach, and other bars stand for our approach. Longer bars here means longer time costs, which is worse. And though our neural network still time out on some benchmarks, the frequency is less. And our neural network terminates on many benchmarks in less than 4 hours. For the number of resolved reports, longer bars means higher precisions. And as the picture shows, our approach resolves more reports than the baseline on almost all benchmarks. And on the benchmark but plot, our approach even achieves a breakthrough of 0. And our overall improvement is over 100%. We also compare the performance of our approach to a state-of-the-art pointer analysis approach. The result shows that our approach can resolve more reports than a pointer analysis approach. But since refinement-based approach tend to be slow, so our approaches are slower than the pointer analysis approach. But this suggests that we could combine those two approaches. For example, we can run the fast pointer analysis first, and then we run the refinement-based approach only on those hard reports. And to figure out why our approach approves such a great improvement, we found that our approach can achieve pruning rates at about 88% to 95%. And for the precision loss, we found that only one of our model has some precision loss, and all of our approaches are faster than the baseline. And to check whether our combination of GNN and MaxSet is necessary, we run the abstraction refinement using neural network alone without MaxSet, and the results are shown as green bars. Its results on most benchmarks are bad, and on some benchmarks, the abstractions are overly precise that even raise out-of-memory exceptions. So this proves that our combination of GNN and MaxSet is necessary, and this combination inherits the strengths of neural network and MaxSet while avoiding their weaknesses. In conclusion, our approach makes use of hypergraphs generated by Datalog, so it could be applied to different analyses without feature engineering. And then we combine the neural network with the MaxSet solver to determine exact refinements. And that's all for today's present.
All right, we have time for a couple of questions.
Thank you for the talk. I wonder how large your programs were in your training set, and two, how you could determine that alerts were real or spurious, whether there was a golden data set for that, or did you have to do some kind of manual process to classify that?
So the first question is how large are our benchmarks, right? Yeah, we choose some small benchmarks from the Datalog benchmarks, and we train our neural network on those small benchmarks, and we found that it could generalize well to large programs that are unseen when training. And I'm sorry, I did not get the second question.
So how large was that? 10 lines, 100 lines, 1,000 lines?
Oh, it should be hundreds of lines, I think.
Okay, and the second question, did you actually do manual classification of the alerts, or did you have some automated way to do this so you know how to refine automatically, or did you have some human in the loop?
Okay, so we just, so you just asked how we generated the training set, right? Or
For the alarms signaled by the pointer analysis, how did you know whether there were false alarms versus real alarms? Is that?
Okay, so for small benchmarks, like we shown here, since they are small enough, the baseline approach can terminate. And due to the property of abstraction refinement, it will refine the abstraction until it cannot refine the abstraction more. So all false alarms will be resolved on those small benchmarks. But for large benchmarks, since the baseline cannot terminate, it does not promise to resolve all false alarms. So that's why our approach can resolve more reports than the baseline on large benchmarks.
Thank you.
Okay.
Very interesting talk, thanks. I know that it's usually a very difficult and difficult question to ask what a neural network is learning, right? And nobody usually has a very good answer. But here I was curious, what concepts is the neural network learning? How does it know when to suggest a refinement and when not to? Did you do any kind of analysis on what is actually being learned?
So did you ask for whether we have done, whether we have tried to explain what the neural network learns? Okay.
Exactly.
We have tried and we found it learns some complex patterns. We know they may be helpful for program analysis, but it's hard to conclude in neural language in several sentences. But we found those features it learns are quite meaningful. We have done such explanation in our paper. But since there are not conclusions that could be taken away, so we do not show those results there.
Okay, thank you.
Okay, let's thank our speaker again, and then it's time for lunch.